Right now, in a desert in northern China, there is a nuclear reactor running with no water inside it. Not a drop. And here is the wild part. If something goes wrong with it, it does not melt down. It does not explode. It does not even need a person to shut it off. It just quietly drains itself into a tank and turns solid, like water freezing into ice. No sirens, no evacuation, no disaster movie ending. That might sound like something from a sci-fi film, but it is real. It has a real license from a real government safety board. It has been running for years, and in the last 2 years, it has hit milestones that no machine on Earth has ever hit before. This is not a rumor or a rendering. This is a working reactor, and it is about to change how the whole world thinks about nuclear power. So, how does a nuclear reactor turn off by itself with no power, no pumps, and no one pressing a button? That is exactly what we are about to break down, step by step. But before we get into the good stuff, if you like learning about wild science that is actually happening right now instead of just theory, hit subscribe. This channel is where we dig into the strange machines quietly reshaping the future before anyone else is talking about them. To understand why this reactor is such a big deal, we first need to talk about why normal nuclear power has scared people for 70 years. Section 2. Why nuclear power scares us here is how almost every nuclear reactor on Earth works today. Scientists take uranium and shape it into solid rods. They stack those rods together in a big tank of water. The water keeps everything cool while the rods react and make heat. That heat boils water into steam, and the steam spins a turbine that makes electricity. It works. It makes huge amounts of power without burning coal or gas, but it has one big weak spot. That water is under extreme pressure, way higher than the air pressure around you right now. Think of a soda can shaken up and ready to burst. If the cooling water ever stops flowing, even for a little while, the solid fuel rods keep getting hotter and hotter. They can melt. And when solid fuel melts inside a reactor built for something totally different to happen, that is when you get disasters. That is what happened at Chernobyl. That is what happened at Fukushima. Both were caused by the same basic problem. Solid fuel plus high pressure plus lost cooling equals catastrophe. After those disasters, the world did not throw nuclear power away, but people became terrified of it. Every news story, every documentary, every scary headline about nuclear energy traces back to that one weak point: solid fuel that can overheat, break apart, and release radiation into the air. Engineers tried to patch the problem instead of removing it. They piled on more backup generators, thicker concrete walls, and more layers of safety systems on top of safety systems. Some plants now have 5 or 6 backup ways to keep water flowing if the main system fails. That is a lot of effort just to keep managing one weak point instead of getting rid of it completely. The fuel was still solid. The water was still under crushing pressure. The risk never really left the building. It just got wrapped in more layers of protection, like putting extra bubble wrap around a fragile package instead of building a package that cannot break in the first place. For decades, a small group of scientists believed there was a completely different way to build a reactor. One where the fuel itself could never sit still long enough to melt down because it was never solid to begin with. That idea sat forgotten in an old American lab for 50 years. China just picked it back up and made it real. Here is where it gets interesting. Section 3. The secret ingredient: liquid rock. Instead of solid fuel rods, this new reactor uses something stranger. It dissolves nuclear fuel directly into melted salt, the same basic chemistry as table salt, just heated until it turns into a thick, glowing liquid at around 600 degrees Celsius. That liquid salt is not just the coolant. It is the fuel itself, flowing like syrup through the reactor. Think about what that means. A solid fuel rod can only get so hot before it breaks down and melts. But this fuel is already a liquid. It cannot melt down because there is nothing solid left to melt. If it gets too hot, it simply expands, and that expansion actually slows the reaction down on its own, kind of like a crowded elevator naturally slowing itself if everyone spreads out. Now here comes the real trick, the part that makes engineers grin. At the very bottom of the reactor there is a small pipe. That pipe is plugged with a chunk of the same salt, kept frozen solid by a tiny electric cooling fan. As long as the power is on, that plug stays frozen and blocks the pipe. But if the power ever goes out, even completely, that little fan stops. Within minutes, the plug melts on its own, because the reactor around it is so hot. And once the plug melts, gravity takes over. The whole tank of liquid fuel drains straight down into a set of safe holding tanks below, spreads out, and cools into a harmless solid lump of salt. No pumps, no backup batteries, no control room decisions. Just simple physics, doing the safety job all by itself. It is like a bathtub with a drain that only unplugs itself when the house loses power, so the water can never overflow, no matter what happens upstairs. That single design choice means a Fukushima-style meltdown becomes physically impossible in this kind of reactor. There is another bonus hiding in this design. The fuel used is thorium, a silvery metal that is about 3 to 4 times more common in the ground than uranium. It was actually named after Thor, the Old Norse god of thunder, because of the way it glows when heated. China alone has enough thorium buried under just one region to power the whole country for hundreds of years, maybe longer. And because this type of reactor can keep reusing and reprocessing its fuel while it runs, instead of burning a rod once and tossing it out, it wastes far less material and leaves behind far less dangerous leftover waste than a normal plant. That leftover waste also stops being seriously dangerous after a few decades, instead of staying deadly for thousands of years like waste from a normal reactor. Since the whole system also runs at normal air pressure instead of the crushing pressure inside a regular reactor, there is no risk of a steam explosion either. Picture the difference between a plastic water bottle sitting on your desk and one that has been squeezed and shaken until it is ready to pop. That is roughly the difference in pressure we are talking about here. All of this sounds great on paper, but paper is not the same as a real running machine sitting in the sand. So, let us look at what has actually happened. Section 4. From test tube to the desert. This whole idea did not start in China. It started in the United States in the 1960s, at a lab that briefly ran a small liquid fuel reactor and proved the concept worked. Then funding dried up, the project was shut down, and the whole idea sat locked away for 50 years while the world built thousands of solid fuel reactors instead. China picked the idea back up in 2011, right around the same time as the Fukushima disaster, when the whole world was rethinking nuclear safety. A team at the Shanghai Institute of Applied Physics spent over a decade building this reactor almost from scratch. They had to invent new metal blends that would not get eaten away by hot, corrosive melted salt. They had to build new kinds of pumps that could survive that heat for years. None of it existed before, so they built it from zero. Construction on the actual reactor began in 2018, out near the city of Wuwei on the edge of the Gobi Desert. In June of 2023, China's nuclear safety regulator handed over an operating license, meaning the government officially said this machine was safe enough to run. Just a few months later, in October of 2023, the reactor achieved a real self-sustaining reaction for the first time. By June of 2024, it was running at full power. And here is the part almost nobody outside the nuclear world noticed. In October of 2024, engineers loaded real thorium fuel into the salt while the reactor kept running, without shutting it down, something a normal plant could never safely do. Then, in November of 2025, came the biggest milestone yet. Scientists confirmed the reactor had actually converted thorium into usable nuclear fuel inside the machine itself, essentially brewing its own fuel while it ran. That made it the only operating reactor on the entire planet to pull this off. Chinese state media even named it one of the country's top 10 scientific breakthroughs of the whole year. This reactor only makes 2 megawatts of power right now, barely enough to light up a small neighborhood. But the point was never the electricity. The point was proving the machine could run safely, day after day, and gathering real data that nobody on Earth has collected in over 50 years. And China is not stopping at a tiny test reactor. Section 5. The race is just getting started. China's own roadmap already includes a bigger 100-megawatt version targeted for around 2035, with fully commercial plants aimed for around 2040. Long-term, the country has floated plans for dozens of these reactors by the middle of the century, enough to help power entire regions that never had reliable electricity before. And the reason this matters is bigger than one desert reactor. A reactor that cannot melt down and needs no ocean nearby for cooling water could be dropped into places a normal nuclear plant could never go. Remote mining towns, dry inland regions, small countries without the resources to run a giant traditional plant. Because these reactors also run at very high heat, they could even help produce clean hydrogen fuel or clean drinking water from the sea someday. China is not the only one racing toward this future either. In the United States, a company called Kairos Power just got approval to build its own salt-cooled test reactor, the first new type of reactor allowed to be built there in over 50 years. A company in Denmark is chasing a similar goal too. This has quietly turned into a global race, and right now, China is the only country with a molten salt reactor actually running under a full operating license. Nobody can say for certain yet whether this technology will end up cheaper than solar power or natural gas. The corrosion problem still needs decades of testing to fully prove out. But the fear that has followed nuclear power since Chernobyl and Fukushima, the fear of meltdowns and mushroom clouds of steam, might finally have an answer. Not a promise on paper this time. An actual machine, quietly humming away in the desert, proving it one day at a time. So here's my question for you. Do you think reactors like this one will actually replace old-school nuclear plants in your lifetime, or will they stay a small experiment forever? Drop your honest answer in the comments. I really want to know. If this changed how you think about nuclear power, smash that like button, subscribe, and turn on notifications so you do not miss the next one, because this story is far from over. And if you want to see how the old Fukushima and Chernobyl disasters actually unfolded step by step, check out that video next.